next up is pressure, and the pressure exerted on a surface is defined as the force exerted on the surface divided by the area the force is exerted over. Pressure is measured in pascals, that's the standard unit, where 1 pascal is 1 Newton per metre squared. Now, you'll be familiar with reducing pressure by having a larger surface area and increasing pressure by having a smaller surface area. New to A level is the idea that this force is perpendicular to the surface. So, for example, if I have, let's say this is a brick resting on a sloping roof, say. There's the weight force exerted by the earth downwards on the brick. That's pulling the brick down and making it push onto the roof of the house. But the weight force is not perpendicular to the roof. And so the normal contact force that the block exerts on the roof will only be the perpendicular component of the weight. And it's this force, this perpendicular component, that goes into that formula. And if you think about it, this makes perfect sense, because the parallel component, obviously that can't be pushing down. If it's parallel to the surface, it can't be pushing on the surface. If you were a crab at the bottom of the ocean, this is meant to be my crab, it's easy to see how all of the water above the crab is pushing down and exerting a pressure on the crab. In the same way, we are actually walking along the bottom of an enormous ocean of air. So there's, miles, I think, of air above us. And because of its own weight, it's squashing downwards and pushing down on us. And incredibly, the pressure on us, because of all the air hitting us, touching us, pushing down on us, is actually 101,000 pascals. Standard pressure at sea level, which is a huge amount, really. It's very surprising, but nonetheless true. But there's an important difference between the pressure exerted by the air on us and the pressure exerted on the water, on the crab by the water. So let's say you're right at the edge of the Earth's atmosphere, and then you're going to go deeper and deeper into the atmosphere, so you're going to have more and more air above you. The pressure is going to increase non-linearly, and that's because the gas particles get squashed together, so that the gas gets more dense as you come further and further down. Whereas for water is incompressible. So if you're at the surface of the sea and then you head down deeper and deeper underwater, the increase in pressure will be directly proportional to the depth that you go. So gases, liquids. And this relationship leads to our formula for the change in pressure on you as you descend a height h into a liquid of density ρ. So that's the formula. So if I go down, say, 5 meters downwards in water, then the change in pressure on me will be the density of water times Earth's gravity times the change in height there. As an unrounded answer there, I'm not worrying about significant figures. Now, the very important thing to note here is that this change in height is the change in vertical height. So if you were going, say, if you were water going down a pipe like that, it's not this distance that matters. It is actually the vertical height that you have dropped by. And bearing that in mind, have a go at this question. Okay, there's quite a lot to say to explain how this situation is happening, but we're going to answer the question first and then come back and talk about it. So what they're clearly expecting you to do, they're trying to catch you out here. They're expecting you to go, change in pressure is rho G, change in H, and so they're expecting you to go for A. Or perhaps even you're going to read this line. It has a cross-sectional area double to that on the left-hand side, and that's just a red herring. So they might be expecting you to go for this one with the 2 in it, but as I say, red herring. We know that this is the vertical change in height. So if you go from there to there, your vertical change in height is this here. And that is H cos theta. So our actual difference is rho G H cos theta. And that means that the correct answer is C. Okay, but now, what's actually happening here? Anyone who's off to be an engineer, this is going to be very relevant to you. So this is a tube that's open at this end. So the pressure here is atmospheric pressure. Atmospheric pressure, I'm going to call it. Then as you come down through the fluid, the pressure is going to increase. As I go along there, it's not changing because I'm not changing height. And that's going to decrease a little bit as I come back up to there. And whatever the pressure is here, that's the pressure exerted by the gas. So I might just call, let's call that GP, so gas pressure. Now what this formula tells us is that the pressure changes when the height changes or when the depth in the fluid changes. So here you are the same depth in the fluid as you are there. You're the same height. So whatever the pressure is here, it must be the same here because you're at the same height. Okay, and so that means that the difference between the gas pressure and atmospheric pressure is due to this water here. And then with our formula, we calculate what that difference is. Let's just say that the difference in pressure there was 500 pascals. That means that the gas is being pumped in here at a pressure 500 pascals higher than air pressure, atmospheric pressure. And that it's that higher pressure that's able to push the water up there.